Okay, our next speaker is Professor Greg Boebinger from the State University and the National High Magnetic Field Lab. And he will talk about, it's interesting, when we won against the referee B, there's something that we all excited to know what is going on. Okay, please. Yeah.
Well, it's certainly, I mirror the previous speakers, what an honor it is to get together and talk about so much great science, but to honor Allan at the same time. Just this morning, Jim Eisenstein gave a brilliant overview of the golden age of double quantum wells in gallium arsenide. I'll be speaking about the Bronze Age here today. And when I went and looked back at my CV, I realized even though we've interacted many, many times, we've only co-authored one paper. And that's the story of this talk here. So I brought my talk on viewgraphs. If any of you young people want to come and see what one of these looks like, I have one here for you. But I'll be talking about the first double quantum wells that Lauren Pfeiffer and Ken West grew, and a lot of the effort was in making sure that the samples were actually behaving like double quantum wells. So these are sort of the average densities, which would be about 160 angstroms between the electrons. The tunneling between the two states obviously depends upon the barrier width. We kept the well widths fixed at a value that optimized the mobility of the electrons. And the barrier widths varied between 28 and 51 angstroms, which would give a tunneling gap somewhere between 4 Kelvin for the less tunneling sample, the wider barrier, and 17 Kelvin for the sample with the narrow barrier. So shortly after this work, I left gallium arsenide double quantum wells before the golden age really started. I had cast my lot with building high field magnets, building pulsed magnets, and while I was working hard to increase the magnetic field by factors of 20 or 30%, Lauren Pfeiffer was reducing the carrier density in the samples by an order of magnitude. So all the physics that was up at 60 Tesla was now showing up at 6 Tesla, and I needed to find a research field where the energy scale was set by God rather than Lauren Pfeiffer. And so I moved into high temperature superconductivity, and hopefully that will work out for me. The outline of the talk is in the beginning, and then a section on the experimental data, the missing integer quantum Hall states, and then how Allan helped me win one against referee B. So in the beginning, there was light, and light involves magnetic fields that create Landau levels. And these are the original quantum flat bands that Allan MacDonald explored. And then he explored the unnaturally thin and the artificially twisted. And this has created so many other quantum flat bands that we've heard about that Allan MacDonald is now exploring and continuing to explore. So after hearing Allan remember every single conversation that people mention, I decided to try to remember one, my first interaction. I don't really know if this was the first, but it was one of the first. We're here because Allan's a great physicist, a sought after teacher, and a nice guy. I have evidence that spans 4 decades. There was an early Aspen meeting. It might have been my first, I'm not sure, sometime in the 80s or 90s. But I recall a delightful afternoon with Allan, and I think Jim was there as well, and a few other people, learning about skyrmions and other stuff. I know it was about skyrmions. The recollection isn't so clear to remind me what the other stuff was. But it was a real opportunity to appreciate how much topology might start playing a role in condensed matter physics. It was when new topological effects were coming in 1s and 2s with quantum Hall effect and then fractional quantum Hall effect. And then skyrmions had just been discovered, Rob Tico's NMR experiments in the 2DEG. But I also have evidence of these 3 facts that date from as recently as a barbecue dinner I had on Sunday with my cousin, Natalie Gray is a first-year PhD student. She's a cousin once removed on my wife's side of the family. First-year PhD student. Thinks she wants to do particles. I worked on her hard. We'll see if that had any impact. But she did mention that Allan is teaching Stat Mech next year, and everybody is trying to get into that class. So the word on the street is out there, Allan, that you're a great teacher. So let's return to the previous millennium. This is paper 16 on my CV, 1990. It was my lab at Bell Labs was still getting set up. There's a preliminary period at Bell Labs, nominally 3 years of duration, where the powers that be decide whether you're fitting in or not, and then they invite you to leave if they think you're not fitting in. So it's a pretty tense time. And I was particularly pleased, and this is a good opportunity to thank Jim again, but thanking all these people because they were loaning me equipment because the lab was still getting set up. And so while competition was high at Bell Labs, there was also incredible collaboration and cooperation. I thank Phil Platzman, Allan MacDonald, Jim Eisenstein, Eric Hellman, who first realized we were seeing the tunneling gap in these double quantum wells, Horst Stormer and Bob Willett for discussions. These are folks because the National High Magnetic Field Laboratory at the time was up at MIT, and a lot of these experiments were done up at MIT in collaboration with Hongwen Zhang. And Hongwen must have been a postdoc of Dan's at the time, but I don't really recall where he was. Double quantum wells. Lauren Pfeiffer and Ken West grew some double quantum wells that Lauren and I kind of sketched out on a napkin, but we had to really make sure that what was being grown was what had been sketched. And this was a tour de force in MBE growth at the time. If you grow aluminum arsenide and then gallium arsenide, you end up having a really dirty interface. And so just single interface heterojunctions were much cleaner than two interface quantum wells. And the idea of having two quantum wells coming together with two clean interfaces and two dirty interfaces, would they still work? It just wasn't at all obvious. So the as-grown samples can be manipulated by gate voltages. And so with zero backside gate voltage, you see there's a beat here. And as you are tuning the backside gate voltage, you get a balanced condition. And I'll show you later why we know that's a balanced condition. I've labeled some of these quantum Hall states. It's a little bit clearer in this sample where you've got a number of nodes of different order, but that beat frequency is what tells you the energy gap or the energy level differences between the two states in the quantum well. And keep in mind, we don't yet know the nature of those states. But there was experimental evidence of 3 different energy gaps of different magnitude. So if we start here at the higher fields, at least in this sweep from 0 to 4 Tesla, nu equals 4 is sitting here. And if we just index every observable minimum, there's a region of relatively high slope here. And then starting at nu equals 16 and going up to 24 or thereabouts, you lose half of your minima. So these are only 2 minima, whereas they were coming in patterns of 4. And if you go to still lower fields, then you lose that factor of 2, and you've got just 1 oscillation frequency. And the physical explanation of these is that here you're only resolving the cyclotron energy, which is much larger in gallium arsenide than the Zeeman energy. And in this regime, you're resolving not only the cyclotron energy, but also the spin split energies, the Zeeman energies. And then over here, with the other evidence that I'll show soon, we know that we're seeing the cyclotron, the Zeeman, and this tunneling gap in these balanced wells. So how do we know that we're seeing that tunneling gap? You just plot the measured densities, the 2 densities that you measure. I've got 2 different samples, squares and circles. I don't know exactly what the difference is between these. I think it was just different thermal cycles. And so the gate bias that you needed to get a certain part on the plot is just slightly shifted. But it's pretty clear that if you've got 2 quantum wells that are not coupled in any way. They're not talking to each other through tunneling. They're not talking to each other through correlations. And also, you know, it's one quantum well here and another quantum well there, and I'm varying the gate bias. Well, if you connect them electrically in parallel, the Fermi energies line up, and you would simply get two intersecting lines here. So here I was tuning the backside gate, so that's the backside gate carrier density, and the front side is nominally independent. But this anti-crossing is what tells you where the density is balanced in your two wells, and it tells you that you've got an energy splitting. And if you convert those carrier densities to energy splittings, you can plot the energy gap between the two electron states as a function of gate voltage. So here's for my narrowest barrier of the three that made it into the paper. Here's my intermediate one. This is the clearest one where you can see there's two regimes. One where you're balanced and you're measuring the symmetric to anti-symmetric gap. The other, when you get far away from that condition and you've got no tunneling, you've just got quantum well states occupied in your two independent wells, and there the energy gap, the energy difference just goes linearly in the gate bias. So the conclusion after quite a bit of work is that Lauren Pfeiffer and Ken West have grown double quantum wells that exhibit sufficient tunneling to observe the energy gap between the symmetric and the anti-symmetric double quantum well states. So the single electron energy band structure features 4 electron states per Landau level. In the high magnetic field regime, the Fermi energy is in the gap dominated by the cyclotron energy. So this would be filling factor 4. You've got 4 energy levels filled in the lowest Landau level. This is the next highest Landau level, so filling factor 8. You're filling 2 Landau levels completely. I should say that then within each Landau level, there's a Zeeman splitting here, G mu B, and then you've got a fan that originates from your symmetric state and another fan that's slightly displaced that originates with the anti-symmetric state. And so for nu equal 2, 6, and 10, you're sitting here, and in the high field regime, that energy gap is dominated by the Zeeman energy. When you're sitting at nu equals 6, your Fermi energy is here, and the same thing applies. The Fermi energy lies in a gap dominated by the Zeeman energy. And for all nu equal odd, the Fermi energy is lying in the symmetric and anti-symmetric gap. So filling factor 1, your highest occupied state is the symmetric state. Your highest or your lowest unoccupied state is the anti-symmetric state. Same story at filling factor 3, 5, and 7. Your highest occupied state is symmetric, and your lowest unoccupied state is anti-symmetric. So these nu equals odd states are the ones we'll focus on, and as the golden age evolved, it became clear that nu equal 1 is the one to really spend a lot of time on, as Jim made abundantly clear in his talk. So we wanted to continue to check that what we've got is what we think we've got. So in a tilted magnetic field at a given filling factor, so these nu equal 4, 8, and 12 states remain unchanged. So the cyclotron energy just depends upon the normal component of the magnetic field. And so if I start here at 0 degrees and I start tilting, this nu equal 4 state just moves out to higher total field. This is the total field because it exists at the same perpendicular field. And that's what governs its energy magnitude. The nu equals 6, 10, and 14 states get stronger. That's perhaps easiest to see here at nu equal 10. It's that minimum that ends up getting deeper. You can also see it here at 16, where there's really no minimum, and then you start to see a minimum when you tilt. And that makes sense because those are the Zeeman energy states. So Zeeman energy depends on the total magnetic field, which is larger at any given filling factor when you tilt the magnetic field. And finally, the nu equal odd states are destroyed. Here's the 5 and the 7 state, and they just completely go away. All the nu equal odd states are gone because they rely on tunneling, which is impeded by an in-plane magnetic field component. So this is all behavior as expected for this double quantum well. So we considered 3 double quantum well samples. We varied the barrier thickness And from the sample with the 28 angstrom barrier width, we see all these quantum Hall states. We went up to the MIT magnet lab, which had fields up to 23 Tesla for resistive magnets at the time. So we see all of the integers. This is not in chronological order, but when we looked at the 40 angstrom sample, the nu equal 1 is missing, whereas all the other states are there. So that's a strange phenomenon. And before we had that sample, we had this sample, the widest barrier. And in this sample, we've got the nu equal 1 and the 3 missing. We've got fractional states, so it's a high quality sample, but the nu equals 1 and the nu equal 3 are missing even in a sample that exhibits the fractional quantum Hall effect. Now, when I showed that data at the cafeteria at Bell Labs, Jim Eisenstein got up and took his socks off. And I didn't really know how to interpret that until just this morning, actually. And so I don't know where Jim is, but thank you very much for that. So to summarize the data on these axes that Jim already presented of the distance between the wells, in this case, the centers of the two wells, versus the symmetric anti-symmetric splitting, as you go along and sweep magnetic field, you're tracing out this hyperbola because the magnetic length is here on both axes. And this just summarizes the data. This line is a hand-drawn line. There's no understanding of what's going on at this point. But we did, after many of these conversations that with the folks that I acknowledged earlier in the talk, we realized that if you've got a very low density sample, and now I'm drawing the electronic wave functions in real space. If you've got a low density sample, then each of your electrons at nu equal 1 will be in the symmetric state. So this is just the charge density of the symmetric state. But if you were to bring the electron density higher, so that the electrons in the plane are closer together, this is real space in the plane, that's the c-axis or the z direction perpendicular to the quantum wells, then the Coulomb energy is going to drive the electrons into individual wells, and it's going to want to put nearest neighbors in opposite wells. And so with that realization that you could have these two regimes, then the question remains, well, why would you get this sort of phenomena? And that comes from the fact that the effective density is not the total 2D density, it's the 2D density divided by the filling factor for the nu equals odd states. And the reason is if you're in the nu equal 1 state, then all your electrons are in this filled level. So your effective density is the 2D density. But if you're up here at nu equals 3, these electrons just give you a uniform charge background, and the only electrons that can play the game are 1/3 of your electrons, namely the ones that are sitting in this energy level. So it's the change in effective density as you go from nu equal odd state to the next nu equal odd state that gets you from one regime to the other. So I made, it's not even a theory, but I basically said, well, let's compare the magnitude of the tunneling energy and compare it to the savings in Coulomb energy if your interparticle spacing is just this in-plane distance versus the diagonal distance. So that's what this is, the in-plane spacing versus the longer distance between electrons. And this would presumably be of order 1. And nu equal odd quantum Hall states would exist if this is the larger quantity. And conversely, there would be no nu equal odd quantum Hall states if the Coulomb energy savings is larger, if this side of the equation is larger. And so when you plot that equation, you get this line. And this is the value, this is where the line sits for a prefactor of 0.6, which is equal to 1. If it were 10 or 0.1 or 100 or 0.01, I'd be concerned. This just shows that something like this could well be happening. And indeed, later on, the understanding in terms of excitons or tunneling states became much more mature. And in fact, the referees didn't like this equation at all. I believe there were words said to the effect of confusion of quantum mechanics and classical mechanics, and it went on from there. Then came word from referee B. So I have referee B's report here with me. I don't carry it everywhere with me. but referee B summarized with the words of death. I recommend that the experimental results and the discussion presented in this letter should be analyzed in a more critical way in a, and here comes the killer, more detailed publication. That reeks of send it to PhysRev B, not PhysRev letters. And so I was a little bit depressed about this. This was early in my career at Bell Labs, but first I want to discuss who could referee B. So referee B would have to be over 60 years old now. And that still leaves a lot of you as candidates. Would have to have worked in semiconductors and or quantum Hall effect in the late 1980s. That narrows the field somewhat. Would not have been working at Bell Labs. That pretty much just rules out Jim. And I'll assume that referee B is not in this room. So Phil Platzman, who was my group leader at the time, had the idea that I should contact Allan MacDonald. So I sent this thing called a fax. And it's called a facsimile, which is a huge exaggeration. It says, thank you, Steve. And the ask was, and Allan had agreed on the phone to do single mode approximation calculations. So I faxed my wish list. I hope this isn't too much, and listed. And then I realized I better give priority rankings in case you can't do it all. I also realized that this single sheet of paper captures the very moment that I learned how Allan spells his name. And this is what the fax returns. It's got, it's not a facsimile. It comes on glossy paper that's got zero coefficient of friction and that spontaneously wants to roll up into a cylinder. But it had all of these results that I had asked for, and I couldn't have been happier. I had dispersion relations for the symmetric anti-symmetric gap versus QL, only one curve per page. But we had these light tables that you could put one sheet of paper on top and one on the bottom, and you could trace. Tracing was an important skill at that stage of my career. And this is the theoretical result that most clearly captures how the nu equal 3 state disappears in just one of the samples. This is the dispersion relation with this minimum at QL of about 1.4, and it finally collapses in the 51 angstrom barrier sample. So this was that better calculation that the referees were asking for. This is the only equation I'll include on the theory, where the phase boundary then actually looks like this. This is if you have no finite thickness. This is if you include the finite thickness of the wells. Allan did this for the nu equal 5 and 7 states, and all of them should have shown quantum Hall effects that match the data. And in general, the data are on the right side of this line once finite well thickness is taken into account, this one outlier here. And Jim showed his later, much more detailed studies of the interesting regime where the tunneling gap drops to 0. But this is what we had at that point. We did some other experiments, and in the interest of time, I'll go through them somewhat briefly. We had a sample as grown that had the nu equal 3 state in it. If you shine light on the sample, the density goes up. The mobility also goes up, and yet the nu equal 3 state goes away. So in a sample with higher mobility, the nu equal 3 disappeared. This is the same sample before and after light. And that gives us one more data point of a missing nu equal 3. So right here is that transition between existing and non-existing quantum Hall state. We then used backside gates and front side gates. This is all data taken at the same temperature, density of 4.19 times 10 to the 11. And then we're increasing the density, and you can see that the nu equal 3 state disappears. The plateaus disappear. And so we were able to measure activation energies here. And the drop is relatively sudden. 25% change in density goes from a robust state to one that's dropped and is no longer visible. I was hoping to get activation energy calculations from Allan, but then I ran into both the precision and the politeness of Allan. In that same fax, he wrote, and I translate here, it would probably be pretty difficult to calculate the activation energy accurately, but I'll try to give it some thought. Regards, Allan. He did not promise to do it. He did not even promise to give it some thought. He promised to try to give it some thought. So if you're still trying, Allan, you're off the hook. I'm not waiting anymore. So why do I say this is winning one against referee B? This again is the message from referee B. This is the key timeline. The experimental paper was submitted in late October. Referee B chimed in sometime in early 1990, and I faxed very shortly thereafter. I faxed the experimental manuscript to Allan on the 20th of February. 1 month later, the theory paper is submitted by Allan. This is my only paper with Allan. 6 days after the theory paper was submitted, the experimental paper was published. And then a few months after that, the theory paper was published as well. So instead of going from one PhysRev letter to one PhysRev B, I ended up going to 2 PhysRev letters. Both I've doubled the citations. And for that reason, I'm deeply indebted to Allan for so much help early in my career, continued wonderful interactions throughout my career. Thank you very much, Allan.
Greg, wonderful story. You may not be a director anymore, but your storytelling ability is still high up there.
Thank you.
An actual question, okay?
Yeah.
I mean, the story is fantastic. There is a possibility, and I would like to hear Allan's opinion on this also, that if you go back to the lab now that you are emeritus director and you have a lot of free
time, if anyone
time,
can make me do it,
lot of free time, and do this experiment at 10 millikelvin,
yes,
you will find those missing quantum Hall state. That possibility is there.
Right.
That it's a crossover physics. Temperature is playing a very important role because you notice in our experiment there is a Q. What is Q in your experiment? You know,
right.
Q, it's disappearing a particular Q. Is the Roton minimum coming out? That is more a signature of Wigner crystal type physics coming in. Is the Hartree-Fock single mode approximation signature for Wigner crystal? That'll be my guess.
Yeah.
I'm not 100% sure,
right.
but let's say I'm 99.99% sure that if you go to, well, if you go to 30 millikelvin, you don't see it, I'll say go to 30 microkelvin.
I know.
So
I know
you're not going to win.
Play. Yeah.
But in any
so
case,
I can
it's
promise...
a serious point I'm making that
no,
your
is,
activation is going down smooth, and I'm not convinced at all it's going to go to 0.
Right.
Okay.
Right.
So I just wanted to make this physics comment.
I'll try to give those experiments some effort.
Yes. Good.
And maybe we can have next speaker maybe come prepare, and we still have some like time for question. Any other question? Or maybe have you ever considered Allan might be the referee V? Because it's until timeline is just too convenient, right?
Oh, only just now. His genius is underappreciated. Actually, there was enough confusion about the experimental details that I think only an experimentalist would get into. It almost certainly was an experimentalist. All my friends are brilliant. I don't know who these referee B people are.